Hello everyone, I am Jai Badrinath Krishnan and I am studying Masters in Mechatronics and Robotics at Schmalkalden University of Applied Sciences. I, along with Professor Dr. Engineer Frank Strudel, developed this paper development of a modern low-cost lab-scale Industry 4.0 plan for education. So here I will be discussing more about this paper in detail on behalf of Professor Dr. Engineer Frank Strudel as well. Industry 4.0 is an arising technology which has proven to increase the production efficiency of industries, which is supported to the graph which we see here shows the development of Industry 4.0 market by region. So the core factor of Industry 4.0 lies in the digitization of the production process through advanced technologies like cloud computing, Internet of Things, big data analytics, advanced robotics, and other cyber physical systems. Industry 4.0 also makes the machines more intelligent by removing the hurdles of communication between the machines. In this project, we will focus more about setting up of an Industry 4.0 plant on a lab scale which mimics a fluid filling plant. The great advantage of this project is that we use various controllers and microcontrollers which in turn would enable anyone to understand how these devices are being used up in an industry. The main aim of our plan is to present as many as possible Industry 4.0 characteristics or components on a comparatively smaller area of 2100 mm cross 750 mm in a modular fashion with relatively lower investment cost. The design behind the Industry 4.0 plan was inspired from highly automated production plants and manufacturing technologies available at Fraunhofer Institute, TU Clausthal, University Labs of Universidad Europea, and RWTH Aachen. The main idea behind the Industry 4.0 revolution is also to improve the production flexibility, that is the ability to produce each product as per the customer's wish, like we see in Adidas Knit for You. Let's understand the concept of the production process through a basic scheme illustrated in the 2D layout. The production process is designed in such a way in order to fill an empty bottle with two different types of liquids based on the customer's requirement. Let's say a customer places an order to fill a bottle with two different types of liquids through a mobile application or an online platform. When the customer places an order, the order is generated and is stored in the manufacturing execution system. This marks the start of the production process. As soon as the order is placed, the robotic arm picks an empty bottle from the storage rack. The bottles in the storage rack are fixed with RFID tags. So the robotic arm moves the empty bottles over an RFID scanner. The RFID scanner scans the production related data such as the production date, time, and the customer's requirement. After this, the robotic arm places the empty bottle over a conveyor. The conveyor moves the empty bottle to the next station, which is a fluid filling station. The fluid filling station is a Festo compact workstation. The Festo compact workstation has various modules including two storage tanks. So based on the customer's requirement, with the help of a centrifugal pump and two solenoid valves, the liquid is filled into the bottle accordingly. This is monitored with the help of a flow meter. Once the bottles are filled, it moves to the next station, which is the quality control station. In the quality control station, the parameters such as the level of liquid filled and the color is monitored. Here, the bottles are marked OK and not OK. Irrespective of the decision, the bottle moves to the capping station. In the capping station, the filled bottles are fixed with the caps. At the end, the Egus robot picks the capped bottles and places it onto the movement robot, which is Robotino. The bottles marked as OK are moved to the customers, and the bottles which are not OK are placed in a separate storage rack. Let's look at the hardware architecture in order to understand the different types of controllers and microcontrollers used in this project. The master-slave technology is used in this project to communicate between various controllers and microcontrollers. The robotic arm uses Arduino Mega as the microcontroller and it communicates with the Beckhoff PLC through digital signals. The RFID scanner is controlled through a Raspberry Pi and it communicates with the Beckhoff PLC through Modbus TCP/IP protocol. The Festo fluid plant as well as the conveyor is controlled through a Siemens S71212 AC-DC relay PLC. It communicates with the back-off PLC using Modbus TCP/IP. The quality station, which is controlled with the help of Raspberry Pi, uses a PiCam and it communicates with the back-off PLC through Modbus TCP/IP. The capping station uses an Arduino Uno and it communicates with the back-off PLC through digital signals. The EGOS robot at the end uses BNR PLC. It as well communicates with the back-off PLC through Modbus TCP/IP. The movement robot Robotino has its own control system and it plans the path in which the robot has to move. The communication between the master PLC and Robotino is through Ethernet. At last, all the data which is happening in the production process is displayed over a monitor. In this project, the synergy between mechanical, electrical, control system, computer science and various other aspects are well supported and maintained. The plan tries to achieve a well balance by interdisciplinary thinking and working that is so essential for the future. For an example, let's consider the custom-built robotic arm. This robotic arm had an involvement of all different modules present here. So on one hand, it tries to give the students a feeling of the complexity of modern industrial production plants. On the other hand, the modular structure tries to keep the complexity of individual components manageable so that the students can learn the plant and carry out experiments within 90 minutes learning units in all aspects. As a whole, this project would give a great insight into a mechatronic system. Let's look more in detail about the robotic arm. This robotic arm was completely designed and manufactured in the university. It is a 4 degree of freedom robotic arm which has a rotational degree of freedom about its base in the z-axis, the yaw, and 3 rotational degree of freedom in the y-axis, the pitch. The gripper of the robotic arm is capable of carrying a payload of 200 grams. So the length of the links were decided based on the robot workspace. After the lengths were decided, the torque at each joints were calculated using the basic physical correlation torque is equal to force into distance. In order to keep the robotic arm compact in size, smaller drives such as NEMA 17 and NEMA 23 were used. Because of the insufficiency in torque, worm gears were used for torque multiplication. One of the advantages of the worm gears is its irreversibility property. That is, this worm gear setup rotates only when the worm gear is rotated and it does not rotate when the worm wheel is rotated. This in turn helps us saving the energy because the robot need not be powered when it has to stay in a position. Let's look at the educational aspects of this robotic arm in the mechatronical aspect. This robotic arm was designed using the SolidWorks software and the torques were verified using the working model software. In order to power the drives, standard motor drives like DM556 and TB6600 were used. These drives have a great electrical concepts such as current chopping, indexing, and microstepping. Another advantage of these drives is that it need not be grounded because of optical couplers. This electrical concept gives a greater understanding of the electrical system. In the programming perspective, the Arduino Mega was used for programming the robot. Arduino IDE was the software which was used to program the robot. As a whole, this robotic arm has a good correlation with the educational aspect of a mechatronic system. Festo Compact Workstation is a modular and a highly configurable workstation provided by Festo for educational purposes. It has two storage tanks for storing two different liquids A and B. A centrifugal pump is used to pump liquid from both the tanks 1 and 2. The compact workstation has numerous sensors for various purposes, but we use the only ones which is required for us in the project. A level monitoring sensor is used to monitor the level of the liquids in the storage tanks. A proximity sensor is used to mark the high and the low levels in the tank so that the tanks can be filled with the liquids when the low level sensor is sensed. A 24-volt DC solenoid valve is fixed to the compact workstation in order to control the liquid flow from the tank outlets. An industrial grade flow meter is used to monitor the flow of the liquids from the tank after the pump. An ultrasonic sensor is used to measure the level of the tank at different levels and fill the liquid accordingly using PID control. This forms a classic example of a control system. In the quality station, the quality of the process is assessed. The parameters used for quality monitoring are the amount of liquid filled and the mixture of different liquid filled. As soon as a bottle reaches the quality station, the Raspberry Pi cam is used to capture the image of the filled bottles. Using image processing techniques, the amount of liquid filled in the bottles can be determined. This picture shows the example of the amount of liquid filled in the bottles. Using color monitoring conditions, the mixture of different liquids filled in the bottles can also be determined. Based on these two results, a decision is made if the product is as per the customer's requirement or not. From this, the product can be decided as okay or not okay. The capping station is a wonderful example of a mechatronic system which uses the concepts of mechanical, electrical and computer science. This capping station was completely designed and manufactured in the university. It uses an ingenious mechanism where only one linear actuation is used to tighten the caps as well as to engage the mechanism with the caps. The capping station has 4 stop positions, each angled at 90 degrees. As soon as the bottle enters the capping station, the process is activated with the help of an IR sensor. As soon as the process is activated, the capping station rotates by an angle of 90 degrees to reach the second position with the help of a NEMA 17 stepper motor. In the second position, the caps are fixed with the caps from the cap storage rack with the help of a servo motor. After which, the table is rotated again 90 degrees to reach the third position. In the third position, the caps on the bottle are tightened with the help of a NEMA 17 stepper motor. The fourth position is the place where the bottle exits the capping station. The NEMA 17 stepper motor is controlled with A4988 motor driver. This project was completely designed with the help of SolidWorks software and manufactured using 3D printing and aluminum profiles. Arduino Uno was used for programming the capping station. This is a perfect example of a mechatronic system, and this can be easily integrated into the course curriculum as a 90-minute module. Finally, in the unloading station, the Igus robot is used to pick the bottles from the capping station. The Igus robot is a 5 degree of freedom robot which is a cost-effective robotic arm. The Igus robot is controlled through a BNR PLC and programmed using Automation Studio software. The gripper of the Igus robot is designed as per the bottle's profile. The Igus robot, after picking up the bottle from the capping station, places it onto a movement robot called Robotino, which is used for the locomotion. The Robotino will deliver the bottles to the customer's pickup point. This marks the end of the production process. In the conclusion, I would like to point out that all the modules present in Industry 4.0 plan will be integrated in the course curriculum as a 90-minute module for students present in the Schmalkalden University of Applied Sciences. This project has proved to be a best example of a mechatronic system and also proved that the complexity of an Industry 4.0 plan can be broken down into 90-minute modules. Currently, all students have access to the modules present in the Industry 4.0 plan. The ingeniously built robotic arm, the capping station, and all other modules has provided a lots of projects and thesis opportunities to the students. Indeed, a lot of challenges were faced during the course of the project. The main challenge was to integrate all the modules together with various controllers through Modbus communication protocol. It is still under progress as it is a bit tricky to establish the communication between all the modules. As an initial trial, OPC UA connection was successfully established. The effects of both this communication protocol will be weighed to find out the best one. The further research of this project would be to monitor the energy consumption of each modules and to transfer those data to a cloud so that the consumption can be optimized. A highly optimized production plant where the process of all the modules can be optimized will be planned. In the future, it is also planned to commission the plant as a remote lab so that the practical experiments can be carried out from a distance by different groups of people without being physically present. I would like to thank Thank you for your attention and please feel free to contact for further information. Thank you.